Unit 6, pages 105 to 111, 20th century physics. Electronic structure of atoms. 20th century physics is going to look at two things. One, that light as a wave travels with a wavelength and an amplitude and a frequency. And light as an electromagnetic wave, the electric field oscillates in one plane and the magnetic field oscillates in a perpendicular plane. The x-axis in the above picture could be either distance at one instant in time or time t at one fixed position. The equation that relates frequency, wavelength, and speed of travel for a wave is going to be wavelength times frequency is equal to the speed of light, where the wavelength has to be in a unit of meters. The frequency must be in a unit of per second, which is the same thing as s to the negative 1, and which is also the same thing as hertz. And then c is going to be the speed of light, and that will be a constant 3.0 times 10 to the 8 meters per second. The Young double-slit experiment demonstrates the wave nature of light. Light is passed through two slits. An interference pattern is observed where the crests of the waves add at certain points. At other points, crests and valleys of the wave cancel, resulting in a dark section of light of intensity. And so here's your light going through two slits, and then they have an interference pattern that's going to give you bright bands of light and then dark bands of light. A baseball can be thrown with any velocity and energy. Most blenders are examples of quantized systems. There is a button for off, chop, liquefy. The blade spins with those energies and nothing in between. Quantum effects are usually not observed in the macroscopic world because the differences in steps are too small to be observed. So, quantum effects. Max Planck explained light being emitted from heated objects. Planck said the atoms in solid objects are like springs that can hold energy. Planck proposed a radical new behavior of atoms where only certain quantized energies are possible. When the energy is released from the solid, it is emitted in the form of light. And so this goes back to up here where you have specific settings, so to speak, and nothing in between. So it's the same thing for quantized energies. We've looked at light as a wave. Now let's consider light as a particle. Albert Einstein, in his explanation of the photoelectric effect, was the first to prove that light can also behave like a particle. So here's the equation for energy as it relates to frequency of a particle of light, which is called a photon. Energy is equal to Planck's constant, which is h, 6.63 times 10 to the negative 34 joules seconds, times frequency, which has to be in units of s to the negative 1 or 1 over seconds or in hertz. Wave-particle duality. De Broglie particle wavelength. De Broglie proposed that particles have wave properties with a wavelength related to the momentum of the particle. And so here you can actually calculate, knowing the wavelength, what is the velocity of the particle with this equation. So this is velocity, not frequency. So to be Planck's constant again, divided by the mass of your particle, which has to be in kilograms, and then the velocity of the particle, which would be in meters per second. And here's just to reiterate that the mass of the particle is in kilograms, and the V stands for particle velocity, which is in meters per second. Davison-Germer experiment. The Davison and Germer proved that particles have wave properties by observing an interference pattern when particles, electrons specifically, are scattered from a copper solid. And so here, it's like doing the double slit experiment except with particles, and then we found that whenever you put the two particles through two slits, we ended up with an interference pattern just like the waves did. Now let's look at the Heisenberg uncertainty principle. Heisenberg proposed that certain quantities could not be measured simultaneously. Delta x means the uncertainty in position, and position, denoted by x, and momentum, denoted by p, cannot be precisely known at the same time. Time and energy cannot be simultaneously measured. Our universe is constructed in such a way that measuring position changes momentum and vice versa. The more accurately x is measured, the more uncertain p becomes. Note this principle is the result of the laws of physics for our universe. A clever device will never be invented that gets around the limitations imposed by the Heisenberg uncertainty principle. Here's an analogy. Suppose we wish to measure the taste of a lemon and the quality of a kiss. As the mind concentrates on the lemon, the mouth gives up on the kiss and vice versa. Measuring one quantity changes the other because they are related to each other. Now let's look at the spectrum of the hydrogen atom. The energy storage ability of individual atoms can be investigated by this simple experiment. You have hydrogen and electrical energy, and then you have an intermediate here where you have hydrogen and then you have light. So analyzing the light, just as in black body radiation, tells us about the energy states of the atom. And so this is where the whole ground state, excited state business comes in, where if you add electrical energy to hydrogen, then the electron is going to move to an excited state, and so this is our intermediate stage, and then the energy has to be given off in the form of light energy as the electron falls back down to the ground state. And we can see that energy in the form of photons. The resulting spectrum consists of lines indicating only certain energy states are possible. The energy states of the atom are quantized. The Rydberg formula predicts the energies of the lines in the spectrum. Rydberg guessed at the result empirically rather than deriving a formula on the basis of some physical understanding of how the atom behaved. So here's the Rydberg formula. The frequency, or 1 over the wavelength, is equal to the Rydberg constant times 1 over the first energy level minus 1 over the second energy level. In this formula, the terms represent frequency of light, and this time it's in centimeters per centimeter, the wavelength of the light, this is the Rydberg constant, and then this is going to be the quantum number of the upper energy level and the quantum number of the lower energy level. It's important to note that Johannes Rydberg, who proposed this equation, only understood the n values as something to make the equation work. He did not understand the significance in terms of quantum numbers describing energy levels in the atom. So here's what's called a Balmer series. And so it's showing you that as energy is absorbed, it depends on how much energy there is in order to reach the next energy level. There is no in between. So that's why it's quantized. And then whatever energy is absorbed is exactly how much must be released. And when it is, we get a line spectrum of different light colors specific to each different element.